Hello everyone. In one of our physics experiments here in IIT-Bombay, we had this configuration. Based on what I thought it can be constructed into a nice JEE Advanced problem. So presenting to you, this is a motor, this is an axle which is rotating, and it is this entire plank is connected to this axle. So the entire plank is going in a circle. There is this one ball which is confined to move inside the plank. So basically there are this edges. The ball can't flip outside the plank. So if you are an observer sitting on the plank, you will just see that the ball can move along the plank. So it can't fall outside. So basically the ball is also going in a circular motion like this. So the entire assembly is rotating with angular velocity omega. The ball is connected. The ball has, say, a mass of smaller. The ball is connected via a string. It's an elastic string. So हम कह सकते हैं it's working like a spring with string constant K. So whatever be its natural length, say L naught is the natural length of the string. After rotation, due to centrifugal force, it gets elongated by, say, delta x. So the final length from here till here, that is L naught plus delta x. That kind of configuration. This is rotating, and that string goes via this pulley and is attached till here. Even the pulley is rotating, so everything is going in this fashion. And this point is fixed here. So if we increase the angular velocity, this will be pushed more outwards. So basically this point will be at its place. This string will get elongated, so pulley will rotate a bit and this ball will come up to here. Now, the question is, suppose the initial length was L naught, and when it was being rotated with omega, the extension was delta x. Now, I remove this point from here and bring it z downwards. So I bring this z downwards. The question is, by what amount the ball will go forward? This is the value which we have provided. अगर यहाँ पे रखा था, angular velocity change नहीं करा. यहाँ पे था, omega से घूम रहा था. The initial length was L naught and the extension in the string was delta x. The final length was L naught plus delta x. अब जब इसको घूमते घूमते, if we take this z downwards, then in steady state, मतलब in steady state या in equilibrium, the ball, we are not considering any oscillations at all. If we bring this z downwards, the ball will get in an equilibrium at this point some distance away. What's that distance? So one of the options you get is z. I take this z downwards, it gets z forward. Option B is not equals to z. Some other equation in terms of k, in terms of omega, in terms of mass, L naught, delta x, in terms of all this. So obviously z won't be an answer. This is an answer and we have to find that equation. So let's try doing it. I'll go by first. One is conventional method and second I'll touch upon is a Mentos-Zindagi method. Let's see that after. First, let's assume initially the radius was r. Initially, let's say the radius was r naught. So I can say L naught plus delta x, that is the total length of the string, is equals to initial height h naught plus radius r naught in the first case. That's the first equation. The second equation which we get is when this is brought z downwards, say this goes by delta, this goes by delta x. Delta x I have already taken. Let's take this. It goes further by delta. So I can write initial length was L naught. The extension now say is delta x1, x2 say. Initial delta x1 was the extension. Now L naught plus delta x2 is the total length of the string, which is equals to h naught minus z plus r naught plus delta. In the second case, when I brought it z downwards, to this length plus this length is this equation. One more equation I get using balancing the force equation. Let's sit on this frame. Then in his frame, you can say that centrifugal force is balanced by the tension in the string, and the tension in the string is equals to K times its extension. So for this first case, K times extension is delta x1 is equals to m r naught omega square. Third equation. Let's write it 1.1. Also from this I can say K times delta x2, because delta x2 is the extension in the second case. The string natural length से delta x2 times बड़ी है in the second case. K times delta x2 is equals to m, radius is r0 plus delta r times omega square 2.1. Now what I can do, let's subtract 2.1 and 1.1. So K times delta x2 minus delta x1 is equals to m delta r omega square. First, this important equation. From these two, if I subtract them both, I get delta x2 minus delta x1 is equals to here h0 will get cut, r0 will get cut. I can get delta r minus z. I hope so. That's the equation which gets established. Delta r minus z is the value of delta x minus delta x1. Put this value into this. So what I effectively get, K times delta r minus z is equals to m omega square delta r. So I divide this K here, delta r. So from that I can get delta r. Have I done it properly? This is delta r minus z divided by K is m delta r omega square. So delta r 1 minus m omega square by K is equals to z. So I can say delta r, the change in the radius I get is equals to z over 1 minus m omega square by K. This is the answer. What does this mean? अगर आप पहले ऐसे ये बॉल घूम रहा था ऐसे, after you bring this z downwards, this goes forward by a value which is much greater than z. And why does this conceptually happen? You can see now, if you get this down by z, if you say this goes forward by z, but now centrifugal force has increased, m omega square r, radius बढ़ गया. Since centrifugal force has increased, it will try pushing it farther away to compensate the string force, because string extends in the ज़्यादा होगी, it can compensate for the increase in the greater centrifugal force. So this is what basically we get. It's always greater than z. Only if omega is equals to 0, if this was stationary, if you bring this down by z, then logically kind of we can say that this will go forward by z. But that's not the case in the normal. You can even try exploring what will happen if I said omega is equals to root k by m. This is a special kind of number. We always encounter this in a simple harmonic motion. Omega equals to root k by m का यहाँ पे फील्ड देके देखो क्या होगा. omega equals to root k by m. Omega equals to root k by m is, suppose irrespective of this, at a steady state. Yeah, like let's sit on this rotating frame of reference. If you keep this and if this omega equals to 0, so this reference frame is itself an inertial frame of reference, then if you pull this apart by small amount and leave it, it will perform simple harmonic motion. It will kind of not, because only in the extension kind of thing the string will have a tension. In the compression kind of thing it won't have a tension. Tension chala jayega. It's not a spring. Spring can be compressed, string can't be. But more or less you can get an idea that oscillation has a frequency somewhat about root k by. If you plug that value here, you get delta R is infinity. So I urge you all, try some, take a pen and paper, keep wondering what is happening, what's the discrepancy which is happening, which is making delta R infinity, and what's the physical perspective of this, making this angular oscillation frequency same as this rotational frequency, and why is this disaster happening. So till then, can you try this out? So now let's try the Mentos-Zindagi method. In this, let's say initially ये कुछ radius पे it was rotating, and this is the state of equilibrium. इसका equilibrium नहीं है, and equilibrium मतलब it's not moving with respect to this frame, ठीक है, with respect to the rotating frame. It's stationary, just going in a circle. No radial motion is there. Now, suppose we bring this down by z. If we bring this down by z, let's say this goes further by delta r. This is down by z, this goes further by delta r. So I can say the net change in spring length, string I should say, spring length का change जो है, that is how much, delta r minus z. String length change मतलब positive one, the string increased by delta r minus z. So we also know spring force या string force magnitude is equals to k times extension. So the change in string force, well, initially there was some string force being applied because there was already some extension, but since we change the extension, so for every change in extension, the change in string force is equals to k times change in extension. So the change in extension is basically the change in string length, क्योंकि initially string इतनी थी, suppose this is the natural length, in the case one it was extended up to this, now it is extended by this. So this to this, that point is the net change in spring force, which I can write is equals to k times delta r minus z. Now from this point to this point, there is also some change in centrifugal force. Centrifugal force increased from this point to this point. So what is centrifugal force? Centrifugal force is equal to m r omega square. So change in centrifugal force is equal to m, change in the radius. This was initial radius, this is the final radius. So the change in radius is how much? Delta r, m delta r omega square. Both are positive. So string का force भी बढ़ गया, centrifugal force भी बढ़ गया, और दोनों equal होने चाहिए. Initially दोनों same थे, finally भी दोनों को same होना है, तभी तो system अपने equilibrium पे रहेगा. I can just very well equate m omega square divided by k times delta r is equal to delta r minus z. Just ignoring some of the steps. So z is equal to delta r 1 minus m omega square by k. That's the same answer which we have got here. So for conceptual clarity, the conventional methods are not just required, they are mandatory, but for acing papers like JEE Advanced which have a time constraint on your head, this is what you must aspire for. So in the next segment I will come up with a more modification on this. The hint of which I give is, say we take this, in the next segment I will cover, forget that we are bringing it down by z, just remember this setup, and at this setup when this is rotating with omega, the mass of this is m, and what else, this radius say is r0. Yeah, I guess that's sufficient. Now in this setup, if in this frame, so if you sit on the rotating frame, and in your frame if this point is pulled outside by some amount, it will perform a simple harmonic motion. I don't know if it's a simple harmonic motion or motion of what kind, but you have to give me the time period of oscillation of that motion. So don't forget there will be centrifugal force into consideration, there is also this spring force into consideration. And after getting this, I guess this is a simple equation. After getting this, find, suppose this is displaced by amplitude A, find trajectory of ball in ground field. This is something which I expect would be a bit difficult, bit challenging, but very interesting something to see. Thank you very much.